Welcome to today's problem walkthrough. In this session, we'll explore LeetCode problem number 672, Bulb Switcher 2. This is an interesting and thought-provoking problem that challenges us to think critically about how operations affect a system of bulbs. Let's dive in and uncover the solution step by step. In this problem, you are given n bulbs that are initially turned off. These bulbs are numbered sequentially from 1 to n. The task begins by turning all the bulbs on, and then you have up to m rounds to perform a series of operations. There are 4 possible operations you can choose from in each round. You can toggle all the bulbs, toggle only the bulbs with odd indices, toggle the bulbs with even indices, or toggle the bulbs whose indices satisfy the condition k%3 = 1. After performing up to m operations, your goal is to determine how many unique configurations of bulb states are possible. The input specifies the number of bulbs, n, and the number of operations, m, and the output is the count of unique configurations that can be achieved. To understand this better, let's look at some examples. First, consider the case where n equals 1 and m equals 1. With only one bulb, we start with it turned off. If we perform one operation, such as toggling all bulbs, the bulb turns on. If we perform the same operation again, it toggles back to off. Since there is only one bulb, the only 2 unique configurations are off and on, which gives us a result of 2 unique configurations. Now, let's consider another example where n equals 2 and m equals 1. When n equals 2 and m equals 1, we start with both bulbs off, represented as off, off. If we toggle all the bulbs using the first operation, the bulbs become on, on. If we toggle only the odd-indexed bulb using the second operation, the bulbs become on, off. Finally, if we toggle only the even-indexed bulb using the third operation, the bulbs become off, on. These 3 configurations, on, off, and off, on, are all unique, so the output in this case is 3 unique configurations. Now, let's move to a slightly larger example with n equals 3 and m equals 1. For n equals 3 and m equals 1, the bulbs start in the state off, off, off. Using the first operation to toggle all the bulbs, we get on, on, on. The second operation toggles only the odd-indexed bulbs, resulting in on, off, on. The third operation toggles the even-indexed bulbs, producing off, on, off. Finally, the fourth operation toggles bulbs whose indices satisfy k%3 = 1, resulting in on, off, off. This gives us 4 unique configurations: on, off, and on, off, off. Additionally, it's important to consider constraints such as cases where m equals 0, meaning no operations are performed, or when n equals 1, which limits the possible configurations. For larger values of n and m, the interaction of these operations creates patterns that allow the problem to be reduced to a smaller state space, making it computationally manageable. In this problem, we are tasked with determining the number of unique configurations of n bulbs after performing up to m operations. Each of the operations toggles specific subsets of bulbs. The first operation toggles all bulbs, the second toggles bulbs at odd indices, the third toggles bulbs at even indices, and the fourth toggles every third bulb. The bulbs are initially turned off, and the challenge lies in understanding how these operations interact to create distinct configurations. To approach this problem, we can make several key observations. First, the operations exhibit a cyclic pattern because they toggle subsets of bulbs based on their positions. This means that instead of analyzing all n bulbs, we can reduce the problem to only a small subset of positions. For larger values of n, specifically when n greater than 3, the behavior of the bulbs becomes repetitive due to the periodicity of the operations. As a result, we can simplify our calculations by limiting the scope to the first 3 bulbs, effectively setting n equals min n 3. Furthermore, the number of distinct configurations depends heavily on the number of operations, m, and the specific operations performed. This relationship between n, m, and the operations is critical to solving the problem efficiently. One approach to solving this problem is through brute force. Here, we simulate all possible sequences of operations and their effects on the bulbs. For each combination of operations, we record the resulting bulb configurations and count how many are unique. However, this method suffers from exponential complexity, as generating and simulating all operation sequences becomes computationally expensive for larger values of m. To address this, we can turn to an optimized approach using bit masking. By limiting the problem to the first 3 bulbs, we can represent their states as a bit mask, such as 0000 for all bulbs off or 111 for all bulbs on. Each operation modifies specific bits in the mask, and we use a set to track distinct configurations. This method is highly efficient, as the number of possible states is small, allowing us to compute results in constant time without unnecessary computations. A deeper mathematical analysis provides additional insights into the problem. By examining how the operations interact algebraically, we can derive the maximum number of configurations for different values of m and n. For example, when no operations are performed, m equals 0, there is only one configuration where all bulbs remain off. With one operation, m equals 1, up to 4 distinct configurations can be achieved. For 3 or more operations, m equals 3, and when n equals 3, the number of configurations reaches a maximum of 8. This analysis helps us understand the inherent symmetry and constraints of the problem, allowing us to compute configurations without explicitly simulating them. While this approach is elegant, it requires careful handling of edge cases and a thorough understanding of the problem structure. Ultimately, we select the optimized bit masking approach for its balance of efficiency and ease of implementation, with the mathematical analysis serving as a valuable validation tool. Each of the approaches has its own trade-offs. The brute force method, while straightforward, is computationally expensive and impractical for larger inputs due to its exponential complexity. The mathematical analysis is compact and provides elegant insights into the problem structure, but it requires a deeper understanding and is less intuitive to implement directly. In contrast, the optimized bit masking approach combines efficiency with simplicity, making it the most practical choice for implementation. By focusing on the first 3 bulbs and leveraging bit masking to track configurations, we achieve a solution that is both computationally efficient and easy to understand, making it the ideal strategy for solving this problem. In this problem, we are tasked with finding the number of unique states that can be achieved for a set of n bulbs after performing at most m operations. Each operation toggles certain bulbs based on a specific rule, and the goal is to determine how many distinct configurations of bulb states are possible. Now, one key insight is that for small values of n, particularly when n is less than or equal to 3, the problem becomes much simpler because the operations tend to overlap in their effects. Beyond n equals 3, the behavior of additional bulbs essentially repeats, meaning that analyzing just the first 3 bulbs is sufficient. This allows us to reduce the problem to cases where n equals min, n, 3. Next, we have 4 types of operations that can be performed to toggle the bulbs: toggling all bulbs, toggling only the odd-indexed bulbs, toggling the even-indexed bulbs, and toggling every third bulb. Each operation has a unique impact on the state of the bulbs, and understanding these effects is key to solving the problem efficiently. To represent the states of the bulbs, we can use a binary format where each bulb is represented as a binary digit, 1-4 on and 0-4 off. For example, the first 3 bulbs can have states like 000, 111, or 101, which correspond to specific on-off patterns. When we perform an operation, it effectively flips certain bits in this binary representation. For instance, toggling all bulbs flips every bit, while toggling odd-indexed bulbs only affects specific positions. By combining these operations, up to m times, we can generate a variety of states. However, because of symmetry and overlapping effects, many operation combinations may lead to the same state, resulting in redundancy. This is where optimization comes in. The total number of unique states achievable depends on the smaller of n and m. While there are up to 8 possible states for 3 bulbs, not all of these are achievable for every value of m, so we need to carefully analyze which combinations produce distinct results. To solve the problem, the algorithm follows a structured approach. First, we focus on reducing the scope of the problem. If n is greater than 3, we only analyze the first 3 bulbs and let n equals min, n, 3, since the behavior of additional bulbs is repetitive. Next, we handle special cases. If m is 0, no operations are performed, and the bulbs remain in their initial state, meaning there is only one possible configuration. Similarly, if there are no bulbs, n equals 0, the result is 0 states. Once the scope is clear, we define all possible states by considering the transformations caused by each operation. For example, toggling all bulbs flips every bit, and combining operations leads to new configurations. Using a set, we simulate all valid combinations of operations up to m, ensuring we only track unique states. Finally, the size of this set gives us the total number of distinct states that can be achieved. To implement this efficiently, we rely on two key data structures. First, a set is used to store unique bulb states, ensuring that duplicate states are not counted. This is critical for tracking configurations without redundancy. Second, we use binary representation to model the states of the bulbs. This representation is compact and allows us to quickly toggle specific bits based on the operations performed. In terms of complexity, the problem is highly constrained. Since n is reduced to a maximum of 3 and there are only 4 operations to consider, the number of combinations is fixed and small. As a result, the time complexity is constant, effectively O(1) for small n and m. Similarly, the space complexity is constant at O(1) because the set stores at most 8 states, corresponding to all possible configurations of 3 bulbs. This makes the algorithm both space and time efficient. Let's walk through an example to see the algorithm in action. Suppose the input is n equals 3 and m equals 1. Initially, all bulbs are OFF, so the state is 0, 0, 0. Now, we consider the possible operations. If we toggle all bulbs, the state becomes 111. Toggling only the odd-indexed bulbs results in 101, while toggling the even-indexed bulbs changes the state to 010. Finally, toggling every third bulb affects only the first bulb in this case, resulting in the state 001. With m equals 1, we can perform only one operation, so the unique states achievable are 000, 111, 101, 010, and 001. This gives us a total of 4 distinct states. Therefore, the output for this input is 4, which represents the number of unique configurations possible with the given constraints. This solution is designed for LeetCode problem number 672, bulb switcher 2, and calculates the number of unique configurations for n bulbs after at most m operations. Here's the explanation. 1. Base case handling. If no operations are performed, m equals 0, or there are no bulbs, n equals 0, the number of states is 1 because the bulbs remain in their initial configuration. 2. Symmetry reduction. If n greater than 3, the problem simplifies because the operations affect bulbs in a symmetrical way. The states of the bulbs beyond the first 3 do not introduce new configurations. Therefore, we can reduce the problem to considering just the first 3 bulbs, n equals 3. 3. State enumeration. The number of unique states depends on the number of bulbs, n, and the maximum number of operations, m. If m equals 1, there are specific possible configurations depending on n. For instance, with 1 bulb, there are 2 states, while with 3 bulbs, there are 4. If m equals 2, more configurations become possible. For example, with 3 bulbs, there are 7 unique states. If m equals 3, the maximum number of configurations is reached. With 3 bulbs, there are 8 unique states. 4. Return results. The solution uses pre-computed results for all combinations of n and m values within the constraints, ensuring optimal performance. This implementation is concise and leverages symmetry and pre-computed values for efficiency, making it highly suitable for competitive programming scenarios. This is the Java implementation for LeetCode problem number 672, bulb switcher 2. The logic mirrors the Python solution, with key differences including Java's stricter type declarations and array handling. The implementation handles cases for 0 operations or 0 bulbs, and adjusts for symmetry when n greater than 3. Unique states are returned based on the values of n and m. Here, we start with the example where n equals 1 and m equals 1. The input specifies that there is only 1 bulb, and we can perform exactly 1 operation. We first check for any special cases. Since both n and m are non-zero, and n is not greater than 3, we proceed with the computation. For m equals 1, the solution uses a predefined array, 2, 3, 4, to determine the number of unique states. The value of n determines which element of the array to use. Since n equals 1, we take the first element, which is 2. This means there are 2 unique states possible with these parameters. So, the final output for this example is 2 unique states. When there is only one bulb and you can perform one operation, the 2 possible states are straightforward. You can either leave the bulb in its initial on state or flip it to turn it off. This gives exactly 2 distinct states. Now, moving to the next example, where n equals 2 and m equals 2. Here, we have 2 bulbs and are allowed 2 operations. First, we check the special cases. Since both n and m are non-zero, and n is not greater than 3, we continue. These conditions allow us to proceed to compute the number of unique states without any further restrictions. To determine the number of unique states when m equals 2, the solution uses the array 2, 4, 7. The value of n determines which element of the array to choose. Here, n equals 2, so we take the second element, which is 4. This means there are 4 unique states possible. Let's understand why. With 2 bulbs and 2 operations, you can achieve the following states. First, both bulbs on, which is the initial state. Second, both bulbs off, achieved by flipping all bulbs. Third, the first bulb on and the second off, achieved by flipping only the second bulb. And finally, the first bulb off and the second on, achieved by flipping only the first bulb. These combinations give us exactly 4 unique states. Now, we consider the case where n equals 3 and m equals 3. Here, we have 3 bulbs and are allowed 3 operations. After verifying that both n and m are non-zero, and n is not greater than 3, we move to determine the number of unique states. For m equals 3, the solution uses the array 2, 4, 8. The value of n determines which element of the array to use. Since n equals 3, we take the third element, which is 8. Thus, there are 8 unique states possible. This increase in the number of states is due to the additional bulb and the greater number of operations, which allow for more combinations of flipping patterns. With 3 bulbs and 3 operations, the possible states come from various combinations of flipping all bulbs, flipping only odd bulbs, flipping only even bulbs, and other such patterns. These combinations result in configurations such as all bulbs on, all bulbs off, the first and third bulbs on while the second is off, and other similar arrangements, totaling 8 unique states. Additionally, the solution makes an important observation about symmetry. Since flipping patterns repeat cyclically, the effective number of bulbs can be limited to 3, even if n exceeds 3. This symmetry allows the solution to use pre-computed arrays 2, 3, 4, 2, 4, 7, and 2, 4, 8 to officially determine the maximum number of unique states for m equals 1, m equals 2, and m equals 3, respectively. This approach eliminates the need to simulate all possible bulb flipping operations, making the computation highly efficient. The time complexity of this solution is O(1), which means the execution time is constant and does not grow with the size of the input. Let's break it down step by step. First, the basic checks for conditions like m equals 0 or n equals 0 or simple evaluations that immediately return results if no operations are performed or if there are no bulbs. These checks are constant time operations, taking O(1). Next, if the number of bulbs n is greater than 3, the problem is reduced to only considering the first 3 bulbs because the states of bulbs beyond the first 3 are symmetrical and do not introduce new unique states. This reduction is also an O(1) operation since it only involves evaluating a condition. Finally, the solution directly fetches predefined results based on the values of n and m. Accessing these predefined lists is an O(1) operation because the lists are fixed in size and do not grow with the input. Taken together, all these steps are constant time operations, leading to an overall time complexity of O(1). The space complexity of this solution is also O(1), meaning the algorithm uses a constant amount of memory regardless of the input size. To understand this, consider the following points. The function takes 2 integers n and m as input, and since integers require a fixed amount of space, this contributes O(1) to the space complexity. Then, there are the predefined lists 2, 3, 4, 2, 4, 7, and 2, 4, 8, which are of fixed length, containing only 3 elements each. These lists do not grow with the size of the input, so they also require O(1) space. Additionally, the solution does not use recursion, dynamic programming, or any additional data structures that depend on the input size. This means no extra memory is allocated during execution. With no variable memory usage and only fixed size storage, the space complexity remains constant at 1. When comparing this optimized approach to a brute force solution, the improvements in time and space complexity become clear. A brute force method would involve simulating all possible states for n bulbs and m operations. Since each bulb can be in one of two states on or off, there are 2 to the power of n possible states. For each state, simulating up to m operations would result in a time complexity of 2 to the power of n asterisk m. Additionally, storing all possible states would require 2 to the power of n space. In contrast, the optimized solution takes advantage of symmetry in the problem. By recognizing that only the first 3 bulbs influence the unique states, the problem size is effectively reduced to a maximum of 3 bulbs. Operations beyond 3 toggles do not generate new states due to cyclic repetition. These insights allow the solution to use predefined results for each combination of n and m, resulting in both time and space complexities of 1. This constant complexity is mathematically justified by the fact that the states and operations are inherently limited, and accessing predefined results is always a constant time operation. One common mistake in this problem is overcomplicating the solution. Many people attempt to simulate all possible operations for every bulb, but this approach introduces unnecessary complexity. Instead, focus on identifying patterns and symmetries in how the bulbs toggle. Another frequent pitfall is overlooking the constraints on the number of bulbs, n, and the number of operations, m. When n is 3 or less, the number of states is inherently limited, and you can manually enumerate all combinations of operations to simplify your analysis. Additionally, it's critical to understand the difference between even and odd indices. Remember that in 1-based indexing, odd indices refer to bulbs like 1, 3, and 5, which is something some people confuse with 0-based indexing. A further misunderstanding comes from overestimating the impact of m. When m is 4 or greater, the toggling operations allow you to reach any valid state within the constraints of n, so there's no need for redundant computations. Lastly, edge cases like n equals 1 or m equals 0 are often overlooked, leading to errors in logic. Testing these boundary conditions is crucial to ensure your solution is robust. The key insight for solving this problem lies in recognizing the symmetry of operations. For cases where n is greater than 3, the effects of toggling operations repeat in cycles. This means you only need to focus on the first 3 bulbs to determine the unique states for the entire system. Optimizing your approach involves moving away from brute force simulation and instead analyzing the toggling patterns, which drastically reduces the number of potential states to consider. While brute force may be easier to implement, it's inefficient and doesn't demonstrate a deep understanding of the problem. By leveraging pattern-based reasoning, you can achieve a more elegant and faster solution. In interviews, you might also encounter follow-up questions about how this solution scales as n and m increase. It's important to explain why the unique states do not grow exponentially due to the problem's constraints, showcasing your ability to think critically about the problem's behavior under different conditions. This problem shares similarities with several other problems on LeetCode. For example, in LeetCode number 319, Bulb Switcher, the focus is also on toggling bulbs and determining their final state after a sequence of operations. Another related problem is LeetCode number 1375, number of times binary string is prefix aligned, which involves analyzing patterns in toggling operations. LeetCode number 2028, Find Missing Observations, is another example where reasoning about constraints and limited possibilities plays a central role. Lastly, LeetCode number 89, Gray Code, explores state transitions that are conceptually similar to toggling bits, making it relevant for understanding how toggling operations influence outcomes. Exploring these problems can help you build a stronger intuition for pattern recognition and toggling-based logic. There are several approaches you can take to solve this problem, each with its own trade-offs. First, there's the brute force simulation approach, where you simulate toggling all n bulbs for m operations. While straightforward and easy to implement, this method becomes computationally expensive as n and m grow, with a time complexity of n*m. For smaller inputs, however, this approach is viable. Another option is pattern enumeration, where you analyze the toggling operations and directly enumerate the resulting patterns. This method is particularly efficient when n is 3 or less, as it avoids unnecessary computation by leveraging the problem's mathematical structure. While it requires a bit more insight into the problem, it's optimal for small constraints. Finally, a more advanced technique involves representing the toggling operations as matrix transformations in computing the resulting state. While this approach might generalize to more complex toggling problems, it introduces unnecessary complexity for the current problem, especially when n is small. Choosing the right approach depends on the constraints and your understanding of the problem structure. Great job on completing the problem. To wrap up, we reviewed how the number of unique states depends on the constraints and operations. This problem teaches us how to break down complex scenarios into manageable patterns. Keep practicing, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!